Hello, I am Jennifer Duquilo. Today, we're going to discuss about radioactivity and the decay process. On the past discussions, we learned about the structure and properties of an atomic nuclei. We determined that all nuclei are composed of protons and neutrons. However, an ordinary hydrogen is exempted since it only contains a proton. So this time, we're gonna talk about radioactivity. What is radioactivity? Radioactivity is the spontaneous emission of radiation. To simplify this definition, let us relate it to real-life situation. Imagine you're about to sneeze, but it hasn't quite come out yet. How does it feel? It might be strange to describe, but that is exactly what certain atoms experience all the time. They need to expel or emit the excess so that they could regain stability. So again, what causes a certain atom to emit radiation? Experiments suggested that radioactivity was the result of the decay or disintegration of unstable nuclei. So this means that a certain nucleus needs to emit the excess to be more stable. And what this excess being referred to is what we're going to discuss later. Just a quick review. As we all know that inside an atom's nucleus are protons and neutrons. Protons are those particles that have positively charged, while neutrons are neutral. That means it has no charge. Surrounding an atom is an electron which is negatively charged particles. A nuclei is considered to be in stable form if it is in balanced state. That is, the number of protons and neutrons are equal, and the force that binds the protons and neutrons together is called nuclear force. But what happens if nuclei are unstable? As I have said, protons and neutrons are held together by a glue called strong nuclear force. This strong force cancels out the repulsive electrostatic force of like-charged protons and keeps the nucleus stable. However, the nuclear force has a short range of action and is dependent on the ratio of neutrons and protons present inside the nucleus. That is why instability of an atom's nucleus may result from an excess of neither neutrons nor protons. This gives rise to a series of expansions and contractions, thereby expels a substance with a sneeze, just like our body when we sneeze. A radioactive atom has to eject the excess nucleons by releasing energy in the other forms like radiation. So again, instability of an atom's nucleus may result from an excess of either neutrons and protons. An unstable nucleus tries to achieve a balanced state by giving off a neutron or proton, and this is done via radioactive decay. Since we already grasped the concept of radioactivity, let us proceed to its types. So there are three types of radiation that can be emitted by a radioactive substance, namely the alpha particle, beta particles, and gamma rays. The alpha particle is relatively heavy and emitted helium nuclei. That means when a certain radioactive atom emits alpha particles, helium particles are ejected along with the other particles. Anyway, we're gonna talk this more later on. Beta particles, on the other hand, emitted either an electron or a positron. When we talk of positron, it is a particle similar to the electron in all respects, except that it has a positively charged electron. That is why it is called to be the antiparticle of the electron. The symbol E minus or E negative is used to designate an electron, and E plus or E positive designates a positron. Lastly is the gamma rays, in which the emitted rays are high energy photons. The three different types of radiation can be blocked by various substances. For example, the alpha particles are relatively heavy. They can travel only few centimeters in the air and can be easily stopped by a sheet of paper or a plastic. Whereas beta particles have higher energy and have more penetrating power than alpha particle, but are less ionizing in nature. They can travel through the air but can be stopped by a sheet of metal or even protective clothing. Finally, the most energetic and fatal form of radioactive decay is gamma ray, which can penetrate several centimeters of lead. Now let's talk about decay constant. For a particular decay mechanism, the radioactive decay constant for a nuclide is defined as the probability per unit time that a given nucleus will decay by that mechanism. Observation has shown that if a radioactive sample contains radioactive nuclei, which is represented by a letter N, at some instant, the number of nuclei represented as delta N and decay in a small time interval delta T is proportional to N. That means the number of particles that decay in a given time is proportional to the total number of particles in a radioactive sample. The radioactive decay constant is usually represented by the symbol, it's like an inverted Y. In the equation below, the negative sign signifies that n decreases with time, so that means delta n is negative. Remember that the decay constant depends only on the particular radioactive nuclide and decay mechanisms involved. It does not depend on the number of nuclei present or any external conditions such as temperature. To determine the decay rate of a certain radioactive nuclei, the equation presented is used, and that the decay rate or activity of a sample, denoted by a symbol R, is defined as the number of decays per second. Isotopes with a large decay constant value will decay rapidly, those with small decay slowly. General decay curve for radioactive sample is shown in the figure. So this is the plot of the exponential decay law for radioactive nuclei. The vertical axis represents the number of radioactive nuclei present at any time t, and the horizontal axis is time. It can be shown from the number or from the figure that the number of nuclei present varies with time according to the equation. The equation is negative n is equal to n sub 0 e raised to negative decay constant t, where n is the number of radioactive nuclei present at time t. N sub 0 is the number present at time t is equal to 0, and E is equal to 2.718, which is the Euler's constant. So the process that obey the same as the figure shows are sometimes said to undergo exponential decay. Another parameter that is useful for characterizing radioactive decay is the half-life. The half-life of a radioactive substance is defined as the time it takes for half of a given number of radioactive nuclei to decay. To understand this concept, let us simplify it. Remember that, like the decay constant, the half-life tells us everything we need to know to guess what kind of isotope we might have. This means that, like the decay constant, the half-life gives an estimate of the stability of a particular radioactive substance, and it can thus be used to identify unknown isotopes. Let's take for example a scientist who collects 20 kilograms of a radioactive isotope with a half-life of 30 minutes. She leaves her lab to meet with a grad student for 30 minutes. When she comes back 30 minutes, she will have 10 kilograms of the isotope remaining. If she then goes back to check on other experiment for 30 minutes, when she gets back, she will have 5 kilograms remaining. In other words, for every 30 minutes that passes, she will lose half of her sample. To summarize, during one half-life, half of a given number of a nuclei will decay, and during a second half-life, half of the remaining nuclei will decay. So this would be 3/4 of the original number of nuclei. So half-life is represented by the equation presented. As for the units, the unit of activity R is the Curie. That is, 1 Curie is equal to 3.731010 decays. The SI unit of activity is the becquerel. 1 becquerel is equal to 1 decays. Therefore, 1 Curie is equal to 3.73 times 10 raised to 10 becquerel. The most commonly used units of activity are the millicurie, or 10 raised to negative 3 curie, and the microcurie, or 10 raised to negative 6 curie. Now, let us proceed to the decay process. We have learned that there are three types of radiation that can be emitted by a radioactive substance, and one of it is the alpha particle or alpha decay. In simpler way, in alpha decay, the nucleus splits into two chunks. A little chunk called an alpha particle, which is just two protons and two neutrons, and a daughter nucleus with a lower atomic number than the initial nucleus. The radiation here is a small chunk, which generally moves away from the nucleus at a pretty high speed. So again, a nucleus emits an alpha particle, it loses two protons and two neutrons. Therefore, the neutron number, which is denoted by N, of a single nucleus decreases by 2. Z, which is atomic number or the number of protons, decreases by 2, and A, or the mass number of a nucleon, decreases by 4. For example, the alpha decay of radium-226. The radium nucleus is initially at rest. After the decay, the radon nucleus has kinetic energy and momentum, and the alpha particle has kinetic energy and momentum. So as you can see, after alpha decay, the mass number of radium was reduced by 4. The atomic number was decreased by 2. Let us all remember that for alpha emission to occur, the mass of the parent must be greater than the combined mass of the daughter and the alpha particle. In the decay process, this excess mass is converted into energy of other forms and appears in the form of kinetic energy in the daughter nucleus and the alpha particle. Most of the kinetic energy is carried away by the alpha particle because it is much less massive than the daughter nucleus. When one element changes into another, as happens in alpha decay, the process is called spontaneous decay or transmutation. As a general rule, the sum of the mass numbers A must be the same on both sides of the equation, and 2, the sum of the atomic numbers Z must be the same on both sides of the equation. Conservation of mass energy and conservation of momentum must hold. Now, let us talk about beta decay. Generally, beta decay, like any other forms of radioactive decay, happens in the nucleus of an atom. And during beta decay, what happens is that one of these neutrons that is hung out the nucleus turns into a proton. In this process, a new electron was made or emitted. This new electron is referred to as beta particles. When a radioactive nucleus undergoes beta decay, the daughter nucleus has the same number of nucleons as the parent nucleus, but the atomic number is changed by 1, which is denoted by the equation. Again, note that the nucleon number and the total charge are both conserved in these decays. As we will see shortly, however, these processes are not described completely by these expressions. A typical beta decay event is shown in the equation presented. So as you can see, the emission of electrons from a nucleus is surprising because in all previous discussions, we stated that the nucleus is composed of protons and neutrons only. This apparent discrepancy can be explained by noting that the emitted electron is created in the nucleus by a process in which a neutron is transformed into a proton. However, in 1930, Pauli proposed that a third particle must be present to carry away the missing energy and to conserve momentum. Later, Enrico Fermi developed a complete theory of beta decay and named this particle the neutrino, or little neutral one, because it had to be electrically neutral and have little or no mass. Although it eluded detection for many years, the neutrino was finally detected experimentally in 1956. The neutrino, the neutrino has the following properties: zero electric charge, a mass much smaller than that of the electron, but probably not zero, a spin of one half, a very weak interaction with matter, making it difficult to detect. The introduction of the neutrino, we can now represent the beta decay process, and with this complete equation, we could probably infer that beta decay comes in two forms. First is the beta decay minus. In beta decay minus, a neutron decays into a proton, an electron, and an antineutrino. And antineutrino is the antiparticle partner of the neutrino, meaning that the antineutrino has the same mass but opposite charge of the neutrino. Second is the beta plus decay. In beta plus decay, a proton decays into a neutron, a positron, and a neutrino. During the gamma decay, the nucleus emits radiation without actually changing its composition. We start with a nucleus with 12 protons and 12 neutrons, and we end up with a nucleus with 12 protons and 12 neutrons. But somehow, radiation gets released along the way. Very often, a nucleus that undergoes radioactive decay is left in an excited energy state. The nucleus can then undergo a second decay to a lower energy state, perhaps even to the ground state, by emitting one or more high-energy photons. Recall that the electrons orbiting the nucleus have high energy levels, and that each time an electron moves from a high energy level to a low energy level, it emits a photon. The same thing happens in the nucleus. When it rearranges into a lower energy state, it shoots out a high energy photon known as a gamma ray, which have very high energy relative to the electron, or to the energy, of visible light. A nucleus may reach an excited state as a result of a violent collision with another particle. It's more common, however, for a nucleus to be in an excited state as a result of alpha or beta decay. So, for this example, we could see that gamma decays undergoes two steps. The first decay is beta emission, in which it releases an electron and an antineutrino. Second is gamma emission. Here, we can see that the composition of carbon was not changed. Before the decay, it has 12 protons and 6 nuclei, which doesn't change after the decay. The C asterisk indicates the carbon nucleus is in excited state. This excited carbon nucleus then decays to the ground state by emitting a gamma ray. Significantly, radioactivity has practical uses, one of which is carbon dating. The beta decay of 14 or carbon 14 is commonly used to date organic samples. It is therefore possible to determine the age of a material by measuring its activity per unit mass as a result of the decay of carbon 14. Through carbon dating, samples of wood, charcoal, bone, and shell have been identified as having lived for 1,000 to 25,000 years ago. This knowledge has helped researchers reconstruct the history of living organisms, including humans, during that time span. Another application is smoke detectors. Smoke detectors are frequent use in homes and industry for fire protection. A smoke detector consists of an ionization chamber, a sensitive current detector, and an alarm. A weak radioactive source ionizes the air in the chamber of the detector, which creates charged particles.